Hi guys, welcome back to the last segment of our lesson. So we've been looking at an investigation one. We then spoke about the theorems where the investigation was actually taking us, right? And those are three theorems. Angle at the center is twice the angle at the circumference. 2, an angle that is subtended by the diameter on the circumference is 90 degrees. And 3, angles on the same segment are equal to each other. Now we're going to try and show this in terms of a diagram and try to see how do I then solve the questions that have to do with this, right? But prior to that, I want to show you there's 3 ways that you can see this concept of an angle at the center being twice the angle at the circumference. And you need to really know all 3 of them, because it's not always that you're just going to see the one that it's from the chord to the center, from the chord to the circumference. At times it is a bit fuzzy, but I know that you will know what to do when you see that. So let's just have a look at it. So I'm just gonna go here. So remember that the main one that I said would be when I have something like this, right? That's the main theorem. This is 2x and that's x, right? But also, this can also be given to us as something like this, right? And this is 2x and that is x. And the reason why these two are one and the same thing, remember the investigation said that you must move this point that side, right? So if you move it until you leave it here, you did not change the angles. The angles are still there and they still have the same relationship. And then the last representation of this is normally when you have an angle like this, center there. Okay, just assume that this is my center here. It's not really drawn to scale. This angle here will be 2x and that angle there will be x, right? So what am I saying? It means I'll be moving this point up until it gets to somewhere here, right? So you know that this angle here will be 180 minus 360 minus that, which will also be twice that. So these are the 3 representations I need you to please think about. Why I'm bringing this up is because the questions we're going to be solving, not all of them show this theorem as this first one that I have here. At times it looks like that, or at times it looks like the C there. Now, the question is, P, Q, R, B, and A are points on the circle, with center O, right? Give reasons why. 1, the angle P, which is this angle, is equals to the angle Q and is equals to the angle R, right? Remember, what did we say? This will be angles on same segment, right? So you please need to think about that. It will be angles on same segment. Also, why is PBQ? So PBQ, I have PBQ. So this angle here, let me just use a different color so we can see the differences. This one here, PBQ, is equals to PAQ. PAQ will be this one there. So you can see also they are both subtended by that PQ there. So it will still be the very same reason as what I have up there. And then the last one is QAR and QBR. Let me maybe use this color here. QAR, which will be this angle here, and they say this is equals to QBR. QBR will be that one there. You can see also they are subtended by this chord there. So you can see it's not always just going to be straight away that it's up there like this, right? And you have your circle like that. No, at times it might happen that it's an angle here and an angle there. You just need to look at where the chord is, right? And whether that chord is the one subtending both those angles that we are talking about there. So, let me go back to that. So the reason why that is the case, what did we say the reason is? This is angles on same segment, right? Segment is normally SEG. You don't really need to write it in full. Similarly with this one, it's the same. Angles on same segment. And then lastly, even with this one, angle QAR and QBR. So if the first letter and the last letter, maybe this is how you can see it as well, and the first letter and the last letter there are also the same, right? It means that the angle in between those two letters is the same throughout, right? And those two letters, these two letters here, they form an arc or a chord, and those two letters form an arc or a chord. So angles on same segment. And then let's look at maybe a question that has values now, where we need to find some values. O is the center of the circle. Remember, you don't assume. I need to tell you that it is the center. Because I said to you last time, monkey see, monkey do does not apply here. Because it looks like it is the center. It does not make it the center. I need to vividly and clearly state for you that O is the center. Or I can say circle center O, or circle O. If I say circle O, it means O is the center. We normally use O most of the time to represent the center, because it's like the origin. So O, origin, right? But you need to be told that it is the center. So please note that. And then passing through the points M, N, P, and Q. And then PON, which is the angle, PON at the center is equals to 109 degrees, right? Now we need to calculate the size of the following angles. 1 and 2, you need to give reasons, by the way. M1, you need to give reasons. And M2, you need to give reasons. So let's do that together. So to calculate the size of N2, right? So I will say in triangle PON, right? PO is equals to ON. And my reason for this is radii, right? And then I know that it means that angle N2 is equals to angle P2. And my reason, in an isosceles triangle, the base angles are equal, right? But that's not what we say. So I will say angles opposite equal sides. And then from there, I can then say that I have 109 degrees plus N2 plus P2 is equals to 180 degrees. The reason for this will be sum of angles in a triangle, right? Therefore, this makes my N2 plus, but I'm just gonna let me make it just 1 N2 because that's what we are trying to find. Because it is equal to P2. I will say 2N2 is equals to 180 minus 109, which will then be 71. And then from there, you divide by 2, it makes my N1, my N2 to be equals to that. Divide by 2 will be 35.5 5.5 degrees, and that will be the angle there, and that's what you will then need to do there. So firstly, this is a radii, they are equal, it makes it an isosceles triangle, so this is equals to that, and then from there, because it's an isosceles, it makes the base angles to be equal. But please, let me just tell you this. Don't use the word isosceles nature of a triangle or base angle. That doesn't exist in Euclidean geometry at this moment. You say angles opposite equal sides. That's why those angles are equal. And then you can then start calculating using the 180 degrees. The size of M1, so I know that N2 is 31.5 degrees. 35, I mean, right? So to find M1, right? M1, you can see that this chord here, or this arc here, is what subtends this angle here, right? And the very same chord is what also subtends the angle M1. You see? So you do need to use your highlighters, guys, to see what I'm saying right now. So what will you say? You will just say M1 is equals to 35.5 degrees, which is equals to N2. And my reason for this will be angles on same segment, and you'll be done with that. And then to find M2, I need a reason for that as well. To find M2, you can see that this arc here, right, subtends that angle at the center. It also subtends that angle on the circumference. Angle at the center and angle at the circumference, they have a relationship of 1:2, right? So it means that M2 will be equals to 1/2 NOP, right? And my reason for this will be angle at, I will just do this for center, equal 2 times angle at circumference. And then from there you can then solve for your M2. M2 is equals to 1/2 into 109 degrees, and this is going to then be half of 109 will then be 54.5 degrees. Yes, I think that will be 54.5 degrees. And that's what you will then need to do to solve that. At the last point here, you don't need a reason, guys, because why? It's just basic algebra and using your calculator to do that. So our summary is circle and angle theorems will be, we have an angle at the center, which is twice the angle at the circumference. The angle in a semicircle is 90 degrees, and also it's converse. And then lastly, the angles in the same segment is what you need to look at. So far we've looked at my radius, the concept of a chord and what it is about, the concept of perpendicular lines there, right angles, we know that, the angle at the center we've looked at, same segment, and also the concept of alternate segment means other segment. We're going to link this to the concept of tangents in our next lessons. I hope that is clear, guys. The theorems that I've looked at so far, angle at the center being twice the angle at the circumference, angle in a semicircle, and angles in the same segment. Please note those. And then you then need to know how to also at times prove those particular theorems as formal proofs. But if you are using them, you don't need to prove them. You just need to state them. And I've shown you what is the short version of how do you say angle at the center twice angle at the circumference, or angle that is subtended by a diameter, or angles that are on the same segment. Guys, as I keep on saying to you, mathematics is food for the soul. I will see you guys next time.